great pleasure to be here. I'm having the time of my life, and I look forward to interacting, maybe not with all of you all at once, but I certainly welcome conversations, especially if you disagree with me. Then we can have some fun. It's an honor to participate in the 25th anniversary series. At Oxford University, 25 is not such a big number, but the last 5 or 6 years have seen explosive growth. And so it's a great pleasure to be able to participate in this series and interact with you and your colleagues. So let me tell you a little bit about infogap theory and its applications possibly to environmental policy. I'm going to be talking about risk and uncertainty and the distinction between them. I will not slander probability. On the contrary, I'm a great admirer of probability. But not all ignorance is probabilistic. That will be a point I will stress. I will talk about the relation between uncertainty and the imperative to do your best. What the hell does that mean when you don't know what's going on? So we'll talk about limits of prediction and the limits of trying to optimize the outcome, and I'll tell you exactly what I mean at great length by robust satisficing. And then I'm going to do 2 examples. One will be both stylistic examples to illustrate what one can learn from an infogap robustness analysis. The first will be about remediation, and the second will be about optimal monitoring and learning. So let me get started and distinguish between risk and uncertainty. Probability is tremendously powerful and useful. We can use probability in many situations if we understand a stochastic process, or have actuarial data, or historical data, or quality control information, or sociological data. In all those situations and many others, we can use probabilistic or stochastic models to represent our uncertainties. And that is what I will refer to as probabilistic risk. In probabilistic risk, the event space is known. I know what can happen. I can model that event space with probability. And that uncertainty is manageable. It's still risky, and it could be very risky. The point is the nature of my knowledge is structured in a probabilistic risk situation. But then comes along this gentleman, Frank Knight, an economist the first half of the previous century already. He was an economist at the University of Chicago, and in his book in the 20s, Risk, Uncertainty, and Profit, he writes that the uncertainties which persist are uninsurable because there's no objective measure of the probability. You are ignorant of underlying processes. You are uncertain about the innovations that will be made, or what your competitor is doing, or what might be brewing under that mountain. To continue that idea, there's this wonderful quotation from a physicist, Wheeler, in which he says, "We live on an island of knowledge surrounded by a sea of ignorance. As the island of our knowledge grows, so does the shoreline of our ignorance." The more we learn, the more we are able to learn. The more we know, the more we need to know. And in this world in which there is an explosion of knowledge, that explosion blasts a huge hole into this vast realm of the unknown. And it is that unknown that Knightian true uncertainty is referring to that's not probabilistic, and I will elaborate on that. So, non-probabilistic true uncertainty. This true uncertainty, in the sense that Knight meant it and that I'm using it, and I refer to it concisely as an infogap, can arise in a number of different forms. One is a discovery. You can discover something that you didn't know about before. You could discover America. Somebody did that once. Before he did it, nobody except the people who had done it before him knew it was there. Let's not get into that. You could discover nuclear fission, which certainly, while it's a very small event, had tremendously large impacts. You could discover Martians. We haven't discovered Martians yet. Well, imagine how surprised we will be when we do. So discovery is particularly important because you can't know what it is until you discover it. That's not probabilistic. The other category, or the second of 3 categories of Knightian true uncertainty is what I'll refer to as invention or innovation. You can invent the printing press, and somebody did that once. That's a material invention that really has profound implications. It put good handwriting out of business. You can invent the idea of ecological responsibility. That's a conceptual innovation. One can see perhaps roots of the idea of ecological responsibility in the Bible. Man is endowed with responsibility for the world, but really it's a very new idea, and this is a conceptual innovation. You can also have social innovations. The French Revolution was a social innovation. So these are innovations or inventions, and you cannot know what innovation is going to happen tomorrow or next year until it happens. That's exactly what is innovative about it. The third category of Knightian true uncertainty I'll refer to as asymmetric uncertainty, and the paradigm for that is an ambush. The ambusher knows where he and the target are, but the target only knows where he is at best. So there is an asymmetric uncertainty there. It's a surprise to the ambushee. Another form of asymmetric uncertainty is a competitor's innovation. You're developing the best mousetrap since mice were invented, and boy, are you surprised when your competitor does it first and better. Natural catastrophes can sometimes also be thought of as asymmetric uncertainties. It's God doing things that he didn't tell us about ahead of time. So these are categories of Knightian true uncertainty, and the critical thing that I'm stressing here is we don't know what the next discovery, invention, or surprise will be. So Knightian uncertainty is unstructured. We don't know the event space. We do not know the event space of a Knightian uncertainty. That's what's inherent in discovery, invention, and surprise. There are no laws here in any axiomatic sense in the way that there are Kolmogor's axioms of probability, for example. I'm a card-carrying optimist, so Knightian uncertainty is manageable, but barely manageable. Having mentioned the word of indeterminism, lack of laws, I want to discuss these two gentlemen. Karl Popper, a philosopher, spent most of his career at London School of Economics, and Shackle, a contemporary, not a collaborator, but he was at University of Liverpool. These guys independently and in rather different ways developed an idea of indeterminism that I want to tell you about because it's the fundamental abstract mechanism by which Knightian uncertainty does its thing. The idea of Shackle-Popper indeterminism is based on two prior ideas. The first one is intelligence. And in this discussion, what I mean by intelligence is that what you know influences how you behave. Intelligent behavior is behavior that is driven, not necessarily deterministically, but influenced by what you know. And that is true of an individual, it's true of an organization, it's true of a group, it's true of various other organisms. The second idea that underlies Shackle-Popper indeterminism is the idea of a discovery. And this, here I just mention the definition of a discovery. What will be discovered tomorrow cannot be known today. Otherwise, it wouldn't be a discovery tomorrow. So these two ideas, intelligence and discovery, combine to determine or formulate Shackle-Popper indeterminism. And that is that tomorrow's intelligent learning behavior cannot be entirely predicted or modeled today. Tomorrow's behavior will be influenced by things that are discovered or invented tomorrow, and we can't know what they are today because they'll be discovered tomorrow. And so today we cannot fully model or anticipate tomorrow's behavior. I don't want to talk, I'm not going to talk about the Newtonian paradigm of physics, but physics envy should be gently pushed out the window. Human affairs do not follow the laws of physics, or even the paradigm of physics that there are universal and stationary laws that govern human affairs. There is always an element of Shackle-Popper indeterminism that undermines the physics paradigm. So infogaps, indeterminisms, these are unpredictable, in a very strong sense unpredictable, and ignorance is not probabilistic. So it's not that probability is wrong. That's not what I'm saying, even though I get quote-unquote quoted saying that all the time. That's not what I'm saying. Probability is tremendously powerful in the domain for which it is relevant. But when we are dealing with Knightian uncertainty, probability is of limited use. So now, having told you what I mean by Knightian uncertainty, and I summarize or call that infogaps in short, let me talk about the question of optimization. We all try and do our best. But what does that mean when we're facing Knightian uncertainty? So, yeah, what does that mean, to do your best? There are two senses in which I will use the term optimization. The first one is outcome optimization. I'll explain what I mean by that. And the second is procedural optimization, and I'll explain that also. And the distinction between outcome optimization and procedural optimization will motivate the methodology for decision making that I will call robust satisficing, and I'll explain to you what that is. So outcome optimization is the optimization of a substantive good that is valuable to you when it emerges. The basic methodology is that you use your best models to predict the outcomes of your decision alternatives, and then you prioritize these alternatives according to those predictions. So you select the option whose predicted outcome is best. And that's very useful under probabilistic risk. Even if the risk is a horrible mess, which is what that graph is supposed to represent, as long as you have probabilistic models, and certainly in a deterministic environment, but as long as you have probabilistic models so that you know the event space and you know likelihoods, you have structured uncertainty, and you can make reliable probabilistic predictions, and then you can optimize in a probabilistic sense. And that's a perfectly kosher thing to do. I'm in favor of it, under risk, when you know probabilities. But optimization of the outcome is not a responsible methodology when you're facing true Knightian infogaps. In those situations, your best model predictions are no good. They're not worthless, but they are fraught with error, and you don't know where those errors are. You're facing unstructured uncertainty, and you have unreliable predictions. And so in those situations, outcome optimization is not the way to go. We will see in the examples subsequently more precisely the fallacy, as long as I'm not going to be polite, why not go all the way, of outcome optimization under Knightian uncertainty. So now let me tell you about robust satisficing. If I'm not going to do what is ordinarily called optimizing, hire your best professor, pay him lots of money, and get him to enlist the best graduate students he can and work them hard as horses for a year and make predictions about the outcomes. If you're not going to do that, then what should you do? That's the idea of robust satisficing. There are other strategies that one could use, even within infogap theory. The other main strategy in infogap is opportune windfalling. I'm not going to talk about that today. One thing at a time. In robust satisficing, you start with two questions. The first question is, what are our goals? And I'll elaborate what I mean by that shortly. And the second question is, how much surprise, how large an error can we tolerate and still achieve our goals? Those are two central questions, and it's the methodology for responding to those questions that I will explain to you and then illustrate with an example. So satisficing means to achieve a critical outcome, to satisfy a specified goal, or perhaps more than one goal. It requires you identifying essential goals. What is it that you need to achieve in order for that decision to have been worthwhile? The sort of pessimistic way of stating it is you ask yourself, well, how bad an outcome could we incur and still not consider ourselves having failed? And the third point to make with regard to satisficing is that it needn't be modest. One can be a very ambitious satisficer. That is, the critical goal or goals that you specify might be very, very demanding. The idea of satisfying a critical goal doesn't mean that we're being modest. We can be immodest in our aspirations. One of the important points that we will see subsequently in the example, however, is that as you become more demanding in your goals, you become more vulnerable to surprise, and it's the quantification of that trade-off that helps one prioritize decisions. So the first question that one has to address in robust satisficing is, what are the goals? The second question is the issue of robustness. I will elaborate on what I mean by robustness, but roughly, I mean, it's an English word. Immunity to our ignorance. The robustness of a decision is an attribute of the decision, but not an attribute of the outcome. The outcome doesn't have robustness. The outcome is already ex post. Robustness is the attribute of the decision, and it is the greatest degree of uncertainty or error or surprise that you can tolerate if you take that decision and still achieve the critical goals that you've specified. So robust satisficing, in fact, does have you optimize something. Remember, the question I started here with was, what does it mean to do your best? Well, in the context of robust satisficing, doing your best means choosing the option that is most robust for achieving the specified goals that you've set to yourself. And that's different from getting the best outcome. It's conceptually different, and sometimes the prioritization of the options will be different. Sometimes you'll choose a different decision, policy, strategy when you maximize your robustness and satisfies your goals than if you maximize or try and maximize your outcomes. So let me now tell you a little bit about what it means to be robust. And to do that, I'm going to draw in several thinkers from the field of military strategy. The first one is Maher Finkel. He's a retired Israeli general. And he wrote extensively in this book on flexibility. He writes the following. The solution to technological and doctrinal surprise lies not in predicting the nature of the future battlefield or in obtaining information about the enemy's preparation, but in the ability to recuperate from initial surprise. So Finkel is talking about a situation where you know you're going to be surprised, or you'd be darn surprised if you aren't surprised, which I guess that makes you surprised no matter what happens. His point is, what you need to optimize is your ability to recover that surprise, of course, presuming you've got a goal in what you're trying to do. So that's his concept of flexibility. And let me augment that with a famous British strategist, Basil Hart, who developed what he called, between the two world wars, what he called the indirect approach. The indirect approach has many different interpretations in Mr. Littlehart's writings, but one of those interpretations is the following. This is a quote: a line of operation which offers alternative objectives. That is, we could get here or we could get there, and his point is we don't want the adversary to know where we're trying to get. It's a plan or dispositions that are flexible or adaptable to circumstances. You want to keep your options open. And in Littlehart's case, that means where you're trying to get. Not that you don't care where you get, but you want to keep your goals open and obscure to the other side. Well, flexibility, as Finkel talked about it, and the indirect approach, as Littlehart discusses it, are complementary. And they give us complementary insights in what it means to be robust to uncertainty. In Finkel's case, he's trying to manage uncertainty. And Finkel is saying the way to survive your uncertainty is to be able to recover when you get surprised. Littlehart can be thought of as saying that we're trying to exploit uncertainty. In particular, we're trying to engender uncertainty in our adversary and then exploit it. So these are complementary approaches, and The reason I bring them in is that they give us some insight into how we can be robust to surprise. And now a third strategic thinker, more geopolitical than strictly military, is Edward Luttwak, an American. I'm very fond of this because he starts out sounding like he's an admirer of the engineers. But wait, the night is young. The scientist's natural pursuit of elegant solutions and the engineer's quest for optimality, I mean, that sounds pretty good, right? Can often lead to failure in the paradoxical realm of strategy. The virtue of suboptimal but more resilient solutions is what is to be stressed in Luttwak's point. So Luttwak is saying explicitly, be suboptimal, which sounds like he's sort of a kook, but he's not. What he's saying is that you don't know what to optimize. You don't know what the context in which you're going to have to use this, whatever it is, needs to be optimal. You don't know the challenges, at least you don't know completely, the challenges that you're going to have to confront. And so you'll optimize for the wrong thing. That's very Popper. Popper's indeterminism is saying that you cannot know the challenges that you're going to have to confront. So don't try and optimize against them because you don't know what they are. What you need is a strategy or a solution that is suboptimal vis-a-vis the outcome, but that is resilient. He uses the word resilient. I would replace it with a different R word, robustness. They're closely related. Resilient solutions. He wants solutions that will get you at least an acceptable outcome, even though you don't know what the challenges are going to be. And then there are another category of robustness concepts, more computational or quantitative. I won't elaborate on them, but of course, we all of us have computers and MATLAB or something like that. So there are lots of things that we can do computationally. But conceptually, what I'm stressing here is the idea of managing uncertainty by having flexibility of response, exploiting uncertainty by not committing yourself to a particular path. That's little Hart. Being suboptimal, don't try and optimize the outcome because you don't know what you're trying to optimize against. That's Luttwak. Robustness is in contrast to substantive outcome optimality. What we want to do in a robust satisficing approach is to achieve specified goals with maximal immunity or robustness against surprise, and don't try and optimize a substantive outcome. I've said that now plenty of times. So now let me get into an example. Very stylized example. The purpose here is not to outline a specific environmental change strategy, but to illuminate some of the insights one can get when you do perform a robust satisficing analysis. I will start with our very own Jim Hall, who discussed steps towards global flood risk modeling. And he wrote, in global risk analysis, scarcity of information means that risk assessments are based on assumptions. We have to assume things because we really don't know, we don't have the full picture. And there are substantive parts, substantial parts of that picture that are lacking. And so we have to assume something. Uncertainties are endemic, model-dependent, and subtle. The bit about subtle is very important. It's very easy when you're modeling your system to make plausible assumptions. Well, you know, it's normal. It's a uniform interval. It's plus minus. We need to think very subtly, carefully. We need to psychoanalyze the uncertainties. That's a critical stage in the analysis, and one needs not to miss the subtleties of the uncertainties. In flood modeling, Jim wrote, a revolution has been taking place. Now all we have to do is fill in the info gaps, pardon me, for the modification. But I'm sure that's what you had in mind. Another colleague that we are familiar with is Professor Maher Allen, who wrote about drivers of peak warming in a consumption-maximizing world. And he stressed the following point, that the existence of at least one technology capable of reducing net CO2 emissions is crucial. And this is important to understand that the existence of such a technology is crucial because we don't know what this technology is or what it will cost to deploy at the necessary scale. Or I'm sure he would add, or I would add, how long it will take or who can do it, and so on and so on. So that we more or less know, in this context, where we want to go, but how to get there is a big uncertainty. And there are fundamental info gaps in that uncertainty. We don't know what the technology is. That means that we're dependent on some innovation, some discovery. This is Karl Popper world. So let me now delve a little bit into this example of remediation and run through a very brief and stylized example. So our goal is to fix or prevent or reduce damage, various types of goals. And the specific decisions that in my example here, which will be a numerical example, are that we need to allocate budgets, sums of money each year for various tasks. That's sort of a generic stylized problem. There are myriad uncertainties. I hinted at a few with the quotes from our distinguished colleagues. One big uncertainty is you don't know what damage would result if you do something or if you do not do something. Intervening or not intervening, and I will focus on that subsequently. Intervening or not intervening can have very different outcomes, and you really don't know too much about what would be the damage resulting from those alternatives. I will also introduce the issue of discounting over time, which is fraught with uncertainty and can have a tremendous impact, as we've seen in the Stern report and other places. You can have conflicting experts. Experts are, one definition of an expert is that he doesn't agree with the other expert. And so when you have conflicting opinions and conflicting theories, conflicting understanding of how the world works, that's a very fundamental uncertainty. And it can be thought of as a Karl Popper uncertainty in the sense, indeterminism, in the sense that someday someone will figure out, discover, invent a better theory. But in the meantime, you don't know what that better theory is. You may be uncertain about what your critical outcomes are. I've stressed that the first question you need to ask is, what are your goals? You may be uncertain about the goals. Are we concerned about economic goals, or maybe subtler welfare goals, or distributional goals? There can be many different goals, and we're not quite sure what our goals are. That's a very important uncertainty, and definitely needs and can be taken into account in the analysis that I'm presenting here. There are lots of other uncertainties. So now let me just contract this all into a very stylized example to show a robustness curve and what it tells me. So I have a budget sequence over time. I'm going to allocate money according to those numbers, F1 to Ft, over a time horizon of t time steps. And I have a loss at each time. Ut is the loss at time step t, which is uncertain. I don't know what the damage loss will accrue in the future. We have estimates, but we don't know how wrong those estimates are. And this is the point at which one needs to consider the subtleties of the uncertainty. Now, I'm not going to be very subtle here because I only have a few minutes left. That's a wonderful excuse. But when you're really doing this analysis, you need to think very carefully about what is uncertain here. And there are many uncertainties, but even in the loss function, one needs to think about what it is that you know and what it is you do not know and how you model that. And in infogap theory, there are many different types of infogap models of uncertainty, and that's where the subtleties come into play. The performance function that I'll consider in my example is a discounted loss, so that F, whoops, no, that's not what I wanted. F is what I've invested in that year, and U is the loss in that year, and it's discounted over time. The loss function is uncertain. The discount rate will be uncertain, not in the first example, but subsequently. So that's the performance function that I will look at in my example here. And I'm going to satisfice the loss. Now, if I was an optimizer, I would try and minimize the loss. But I'm not going to minimize it for reasons that I've explained. I'm just going to try and choose my budget allocations so that the loss is not larger than some critical value. That I know I'm going to lose something, but I don't want to lose my shirt. Okay? Now, how do you know what the threshold L critical should be? Well, either you do or you don't. I can live with either case. Sometimes the critical value of loss is determined exogenously. You know, the governor says, well, okay, here's your budget. You run over that, you're fired. In other cases, the analysis might be geared to the question, well, boss, how large a loss can we tolerate? So then the purpose of the analysis would be to determine what value of this critical loss, this maximum acceptable loss, is feasible, can be reliably guaranteed. And what I'm going to do is satisfy according to that criterion and optimize the robustness. I'm not going to try and minimize the loss. Okay, so the first stylized example is a single time period. And there are two options. Either do something or don't do something. And in this example, my estimated loss, if I don't intervene, if I don't do anything, is 1.1 something million pounds or Lord knows what. And if I do intervene, my estimate is that the loss would be smaller, which is better. Those are estimated losses. And so based on my estimate, I should intervene by spending that amount of money. But also, there are errors on those estimates. And in this case, in this example, the way to interpret those errors are the following. Somebody, my analyst, has come to me and said, well, Yakov, my estimate, if you don't do anything, would be 1.1 billion. Plus or minus about 20%, or maybe more. That's what he's telling me. He also tells me that if you do intervene, the losses are anticipated to be substantially less, about half, but are much more uncertain because we've never done this intervention before. Okay? So the situation that we face here is what I'll refer to as an innovation dilemma. Intervention looks better because its predicted loss is smaller than if I don't intervene. Doing something looks better than just sitting on your hands. But on the other hand, doing something is more uncertain. That's a dilemma. Now, you don't always have that dilemma. Sometimes doing something would look better and also be more or less uncertain, especially when you've done it before. But if you're anticipating doing something that you've never done before, and there are lots of uncertainties, then you are liable to face this dilemma, that what looks better is more uncertain. And the question that I will grapple with and resolve to some extent is how do you resolve that dilemma? So, the question is intervene or do nothing, and how to choose. My question is the methodological question. So to translate that question into robust satisficing, the question would be how much error can I tolerate if I do or if I do not intervene and still satisfice my performance requirement? What is the robustness of these? What are the robustnesses of these two options? So we're going to evaluate the robustness functions. And we will choose whether to intervene or not by choosing the more robust option. Now, let me just pause a minute. I've tried to sell you on the idea of robustness. Achieving your goal over a wider range of surprise would seem to be better than choosing your action over a smaller range of surprise. Let me suggest that that sounds plausible to me. There are also a range of theorems called proxy theorems in which one can prove that the more robust option is also more likely to succeed. That is, robustness has some sort of probabilistic flavor to it, even though there's no probability hiding there. But there are other situations in which more robust solution is not the more likely to succeed. So I just throw this wrench into the works a little bit to raise the question of, well, Yakov, is this robustness thing really all that good? I'm not going to elaborate on that. I would simply say that if you know probabilities, then don't do this robustness stuff. If you don't know probabilities, then I'd ask if you've got a better option than this approach. OK. So these are robustness curves. Let me tell you a little bit about what they say. The horizontal axis is the critical loss. So we'd like to be on the left. That is, a very demanding requirement is a low critical loss, and a lax requirement is on the right. The vertical axis is the degree of robustness. So this is low robustness, and that's high robustness. And these are the robustness curves for the two options. F equals 0 is the do nothing, and F equal 0.09 is the intervene option. The first thing we notice is that these curves are monotonic. They're straight lines because it's a really simple example, but the theorem is that they're always going to be monotonic. And that monotonic trade-off is sometimes called the pessimist's theorem. What is pessimistic about that is that as you demand better outcomes, you become more vulnerable to your uncertainty. Now that's intuitive to any healthy pessimist. More ambitious requirements are more vulnerable to surprise. That's the monotonic increase of those curves. The second point that I want to stress is that these robustness curves both reach the 0 robustness level. They both hit the axis here at various values of the critical loss, different values. And in particular, the zeroing theorem states that for each of those options, if you calculate your best estimate of the loss and then adopt that best estimate as your critical value, which an optimizer would say, well, it's my best estimate, so let's go for that. That really is a fatuous adoption because the robustness for achieving that best estimate in either of those cases is 0. So here we see in the zeroing property that there's no robustness at the estimated loss. In the zeroing property, we see or the infogap critique of optimizing the outcome. If you use your best models to predict the outcome of doing nothing or doing something, doing nothing has that outcome, which is better, doing something has that outcome, predicted outcome, which is better than the predicted outcome of doing something. Preferring something over nothing is not a good preference because those predictions have no robustness. OK. Yeah, so that's that. So the choice would be to choose the option that's more robust for the critical level of the outcome. We're sort of running out of time, so let me speed up a bit. We notice that there's a preference reversal. These curves cross one another. What that means is that if your performance requirement is to the left of that intersection, then you're more robust if you do something, which, by the way, is what the optimizer would do. So if your requirement is to the left of about 1.4 or something, then the robust satisficer would say intervene. The optimizer would say intervene. They'll agree about the action, but disagree about the reason, but they can still be friends. On the other hand, if your requirement is to the right of that intersection, you're more robust if you don't intervene. The optimizer still says, but my predicted optimum is to intervene. The satisficer says, yeah, but you're more robust if you don't. Another point that needs to be made here is that in this particular example, the robustness might be fairly low on this left part. So an important question that I'm not going to address is how much robustness do you need? What is large robustness? That's an important question. I'm not going to address it. Let me skip. This example can be extended, and I'm going to skip all that because I want to get on to my next example. But just to summarize the remediation example, the first thing, and this is the subtle uncertainty part, is recognize your info gaps. That doesn't mean know what you don't know, but try and understand what it is that you don't know. Try and understand the unboundedness, the unbounded potential of the Shackle-Popper indeterminism. Specify your goals, which may be uncertain. And prioritize your options by maximizing your robustness. And don't try and optimize your outcome. OK, that's one example. Let me very briefly run through a second example, whose title is optimal monitoring or surveillance, and emphasize a paradox. We had a paradox in the previous example. That was the innovation dilemma. There'll be a similar paradox here and a similar sort of resolution. So let me briefly explain that. I'm talking about a situation where we're going to be learning something. And by learning, I mean deep learning, discovering new knowledge, not learning French or Newtonian physics, for which you have a teacher and he knows it all. We want to discover new knowledge. So that's going to connect us to Yakov Popper, right? Because we're going to discover something that even my teacher doesn't know. And we want to do that optimally. The number of books written on optimal learning is large. But I'm very skeptical about optimal learning, and that's going to be the point of this example. We want to minimize the time in which we're going to learn, because we're in a hurry. We want to maximize the quantity that we're going to learn, for obvious reasons. We want to minimize the cost or maximize the quality. Those are optimal learning goals. And those are outcome optimizations. And we're talking about Yakov Popper because we're learning something that humanity doesn't yet know. And so the critique, the infogap critique of that optimal learning is it's fatuous. So sort of to relate it to this community, we're trying to learn a new eco-failure mechanism. Or maybe we're trying to learn, is a new eco-failure mechanism emerging? Where is it? What is it? And how fast is it happening? And so on. It's not a specific learning, is that firm emitting this pollutant in that river? We're trying to understand something about the universe. So to focus in a little bit on that, we want to discover or prevent this new eco-failure. We want to do it, we would like to do it, with maximal effectivity. That's the optimal learning bit. And we have a range of alternatives. We could do extensive research. We're at Oxford University, that's what we do. But if we spend all our time learning, then we'll have less time and resource for having an impact. Or we could not do too much learning, and we could just start swinging the hammer. And we'll have a huge impact, but it may not be all that good because we haven't really learned very much yet. The optimal amount of research, and this is sort of an allocation problem, how much egghead, how much pragmatism, the optimal amount of learning, of research, depends on the failure mechanism. But the failure mechanism is what we're trying to learn. We don't know it. And so you cannot optimize. Optimal learning just is it's an oxymoron. The resolution, or a resolution, the resolution that I'm promoting for the moment, and tomorrow I'll talk about maybe sometime one could also do other things, would be to satisfice the effectivity of your learning and intervention and maximize your robustness to the fact that you really haven't learned it yet when you had to make your decisions. That's a procedural, not a substantive optimization. So I'm sure you see the analog to what we were doing before. So the learning people would come back and say, well, we do optimal adaptive learning, or we do adaptive stochastic learning. Fine. I will catch them in the same way, with all due respect. Because when you do an adaptive learning algorithm, you have to choose all kinds of parameters at what rate you adapt and what you adapt on, and you're going to try and optimize that adaptation. Well, but you have the same learning paradox. Same paradox, right. And if you're going to do adaptive learning or stochastic learning or adaptive stochastic learning, whatever you want, the advice that I would have would be to satisfice your goal and optimize your robustness against your ignorance. So let me sum up my talk. I've distinguished between risk, probabilistic risk, and Knightian uncertainty, infogaps. And I talked about Yakov Popper indeterminism, which is a very abstract or generic mechanism which assures us that human affairs are not obedient to the Newtonian paradigm of the physicists. I emphasized the limitations of substantive outcome optimization, or I emphasized that it's very useful if you have structured probabilistic risk, but it's not useful. Outcome optimization is not a reliable or responsible strategy when you have Knightian uncertainty. And I emphasized robust satisficing. You're going to optimize something that's doing your best Doing your best is optimizing your robustness to your ignorance and satisficing your goals. That's procedural, not substantive. And I talked about 2 examples. I'm happy to entertain questions.